Okay, and I'll just put this, and when I do, if you haven't noticed in the videos, guys, I always just put the date on it. So you just have to remember what day you were gone. Okay, we have some students here that want to pass out JAG books, right?
I'm wearing retro stuff.
It's
retro, we're not retro this.
retro. You got to be retro. Gotta be retro. Okay, so get your notes out. Get ready to take some notes. Here we go. Now, I would just continue the notes from yesterday. So I would just continue the notes from yesterday. Remember, you're going to have a major test over this coming up. All right.
We have a test? Oh, yeah.
Coming up over this, so we want to make sure we have this in our notes. Okay, so let me get to where, okay, so question. Okay, so I just want to, you don't have to write this part down, but I just want to talk about it. We'll have Kaylee pull a stick on this. So we have this picture right here. Okay? Will, are you going to write stuff down? You need to probably get your notes out and stuff ready to write down. Okay, so suppose you drag point X along the circle. Is there, does the measure of angle OXY change? So Kaylee, pull a stick. Wyatt. So if I take X and if this was if I could actually kind of make this move and I move X along this circle, is that angle ever going to change, Wyatt? Why not? Why would it not change?
When the radius intersects a point of tangency, it's always a right angle.
It's always a right angle. Do you guys understand that? So that's the whole point of yesterday. It's restating what we just learned. Okay. So today, we're going to learn a new concept today called a circumscribed angle. Okay. Another word, circumscribed, you can think about this. A good way to think, because we're going to do inscribed after this, and we've already talked about circumscribed angles and circumscribed triangles. So angle outside. Angle outside the circle. So an important fact about circumscribed angles are they're angles that are outside the circle. Now, what is the circumscribed angle here? It's an angle formed by two rays from a common endpoint that are tangent to the circle. So what we're talking about is this angle theta right here, where let me just get these letters here. A, B, C, and D, where lines A, B, or we could say rays AB and ray AC. Now, we're not talking about vectors here. We're actually talking about rays are tangent at points B and C. Okay, so remember what tangent in this case. So we're trying to get SOHCAHTOA tangent out of our mind for now, and now we're kind of thinking about a new understanding of the word tangent. Again, those two words do connect later on. There is a connection why we call opposite over adjacent, and then a point on a circle that's touched by a line. There is a connection between that word, but right now we're separating those two words. Yes, ma'am. Yep, quick. Okay. All right. Any questions here? Okay. So does everyone understand what a circumscribed angle is when we're talking about tangent lines? Okay. And you can think about this, guys, just kind of like think about the usefulness of this. Now, this is 2D, but when you're talking 3D, and you can expand this concept a little further, that this is, if A is a satellite, okay, point A is a satellite, and it has, its coverage is going to be, and it would be a cone because it would be 3D, but its coverage of the Earth would be that angle right there. Do you guys understand that? Okay. It can't cover. That's why you have to have multiple satellites and things like that, because the satellite angle is going to be that circumscribed angle out there. All right. And that's huge. I mean, people that study space and satellite and technology and all that stuff, wireless technology, triangulation, all that stuff, they're absolutely using these geometry concepts. Okay. They're huge. All right. So now, here's a huge theorem here. Okay. It's called the Circumscribed Angle Theorem. So let me read this and you can write it down, and I want you to draw this picture here. Okay, a circumscribed angle of a circle and its associated central angle are supplementary. So I want you to write that down. It's very important. And actually, it's a very I don't think we're going to formally prove it, but it's actually a very easily understood idea. Very easy. So I want you to think about this, and I'm going to pull a stick, and I want someone to kind of explain why this is kind of almost obvious that those two angles would be supplementary to each other. Okay, when we're saying we're saying this theta here, right? And we could say this, I don't know how to do a delta. Call that delta. We have alpha, we have theta and delta. Those two angles are going to be supplementary to each other. And it's actually a very easy concept why that would be true. Okay? And then Sam, if you missed this, these will all be recorded, all right? Sound good? Yep.
Am I good to go?
Yep. All right. So I'll give you another second, and then I'm going to have Kaylee pull a stick, and then we're going to have someone explain why that would obviously be true based upon the knowledge that we already have. Okay? Sound good?
Mr. Roden, I've seen delta as a triangle. Is that different in geometry?
Lowercase delta. That's capital delta. Lowercase delta is, I think, this is capital. That's capital delta, and this is lowercase. I think lowercase delta. Yep. Okay. Sophia, do you have a question?
No, I didn't understand your symbols at first. Now I have to rewrite it.
Okay. I just made Greek letters for these angles, and since I already used theta as my favorite, I had to use another Greek letter, so I came up with lowercase d. That's lowercase delta. I think that's what delta looks like. Okay. So, why is this true? Okay, you guys, where you guys are. So geometry is a thinking class. Okay, so we're gonna have Kaylee pull a stick on this one, and I want someone to explain why this is just an obviously true statement. Okay, it is a proof, but we could prove it, but really we can just kind of see why it works. Sometimes an informal proof, or just kind of understand the reasoning here. All right, so Kaylee, can you pull a stick?
Cody.
Who is it? Cody. So Cody, why is this obviously true that angle theta and angle delta are supplementary?
So CXAXB is a polygon / quadrilateral thing, right?
Okay, so we know that so first of all, a couple facts that Cody is saying correctly that I like. So we know that CAXB is just, in this case, it looks like it could be a kite, but we can just say it's a quadrilateral, right, Cody?
Right.
Okay, it's a quadrilateral, probably a kite, but we don't even have to get that specific, right?
Right.
All right, so what does that do for us?
And so in a quadrilateral, the angles have to add up to 360.
So the measure of all those angles, guys, the measure of the angles is equal to 360. So when we take the sum of the angles equals 360. You guys understand that? It's called the polygon angle sum theorem, right? Specifically in a quadrilateral, the sum is always 360. Okay? All right.
And so we know that when a radius intersects a tangent, that gives you a 90-degree angle.
Very good. So what Cody is saying here is we're given, now, here's the thing. We need to know, and did I spell that wrong?
That looks like a rectangle.
Sorry, Will, I didn't mean to make something messy for you. Okay, all right. So what Cody is saying here, class, is we know that these points of tangency and the radii are perpendicular to each other, right? That's what we learned yesterday. So what does that do for us, Cody?
So then we can like add up the angles and subtract that from 360, and we know that the theta and the delta have to be equal to 180 when added together.
Does everyone see that? You got 90 here and 90 here, and you got to have 360. You don't. It's not saying they're equal to each other. It's saying that those two angles have to add up to 180, because the other two already add up to 180 also. You guys see that? Okay. So these right angles are helping us out right there. Okay. So that's good information to know that they're supplementary. All right. So in this problem right here, in figure RQ, what do we got here? We got Q is a tangent point of tangency. What is the measure of angle PRQ? PRQ. So that should be pretty easy. So I want you guys to call this example 1. I want you to go ahead and at least draw this. You don't want to write down the entire problem. And then I want you to figure it out. So this should be a very simple problem. Shouldn't be too bad. Okay. So Kaylee will pull a stick on this pretty soon. Okay.
What's exactly we do?
Pretty soon. Don't give it away yet.
I don't know.
What's 1 week? I'm not sure what you. That's 3 miles.
Oh, of course.
So run.
Okay, Kaylee, give us a stick. This one should be pretty simple.
Martin.
Martin. All right, Mr. Martin, what are we going to do here?
So first, well, what I did first was I drew the problem.
Okay, great. Got it?
The
Yep.
next step is you add 59 and the right angle.
Where's the right angle?
The right angle is angle Q.
Now, why do we know that this is a right angle, Martin?
When a radius intersects a tangent line, it's always going to intersect at a 90-degree angle.
Very good. That's perpendicular. So we've got a right triangle here, right, Martin?
Mm-hmm.
So keep going.
So you add 90 and 59 together. That should give you 149.
Yep.
And then you subtract 149 from 180,
Okay.
and you get 31 degrees.
31 degrees. So pretty easy problem, right, guys? So, I'll maybe throw one of these or two on the test just to make sure give you some easy free points, right, guys? Sound good? All right. Now, this problem I love. Okay, write this down. Give yourself some time and write this down. What we're going to do, and actually, instead of having lines, make it a 2-column proof. Okay, we have not done this problem for a while, so this is absolutely amazing problem here. So this is a statement,
When proofs were done, I was so.
and this is a reason. Proofs are never done.
Dude,
Okay.
proofs are the reason I cry every night.
Okay. So we are going to prove this. So let me read this out loud while you're copying it down. We know that KM and KN are tangent to circle C. How do you show that KM is congruent to KN using congruent triangles? So all of our congruent triangles things, we don't want to ever forget. Now, we don't have the time to prove everything, but definitely this is a very good problem. Again, I love being able to come back to our triangle proofs because it's just the building block of so many good things. So once in a while, it's nice to just go back to it and show you that it's never going to really go away in geometry. Okay. So we're gonna formally prove this, okay? Yesterday we kind of did like an inductive reasoning behind it. It wasn't a proof to show that we have right angles. We didn't prove it. We just kind of assumed it was true, which is not the best thing, but sometimes we do that in geometry just to cut corners. And then the next one we talked about was I think we just talked about why the supplementary rule works, but this one we're actually going to formally prove it. Okay, so I will start us out. First thing I'm going to do is I'm going to say that that angle or point M and N are pots. What does pot stand for, class?
Point of tangency.
Okay, now, why do we know that M and N are pots? Okay, so, Kaylee, pull me a stick on that. Why do we know that they are pots? I'm going to try to get this on one line. Tanner, why do we know that they are pots? M and N are pots. Why, Tanner? What does pot stand for in geometry? Okay, so why do you know that they're point of tangencies? Okay, so it's kind of almost like a given, right? So this is by definition of a pot, right? What is the definition of a pot, guys?
The point where a circle and tangent intersect.
The point where a circle and a tangent intersect. You guys understand that? In geometry, there's other definitions of pot in other places in our life, but in geometry, it's the definition of a pot is the place where the line and the tangent line and the meets the circle, right? Does that make sense, Tanner? Okay, so it's basically the definition of a pot, right? Maybe if we were being really, really picky, we should have probably copied down the given also, right? Okay, but I'm kind of cutting a corner a little bit here. All right, so now what would be the next thing? We got to get congruent triangles here, and I don't see triangles here. So Kaylee, can you pull a stick? This dude needs to tell me, how am I going to go ahead and get a triangle? All right, Miss Tess, I don't see triangles. Could you make a triangle?
Yeah,
How?
we can construct a line through a
Very good. So we can just have segment KC, right, Tess? And what is that? If I just state segment KC, what is that? That's just a construction. I like how you said that. That's very good. It's a construction, Tess, right? So what Tess is saying is whenever we have 2 points, we can always construct a segment through it. We can use a compass, or we can just say that it's absolutely fine. Okay, now, here's the deal. Once we have that, now we can do step 3. Okay, step 3. Tess, why don't you take it one more step? Kind of give it some more. What's another step you can do, Tess? So, M, what? So, let's get an angle in there somewhere. Do we know any angles in there?
Yes, we do.
So angle M is 90 degrees. Angle N.
Ah, very good. So we know that angle M and angle N are right angles, right? You guys understand that? Okay, we know that angle M and angle N are right angles, and we know that from yesterday's theorem, right? What we call this, maybe we'll call it the tangent radius theorem, right? Tangent radius theorem, I think we could call that. Okay, so we can say that angle M and angle N are right angles because we have radii hitting points of tangency. Very good, Tess. Well done. Okay, Kaylee, pull me another stick. What's step 4?
Sophia.
All right, Miss Sophia. Okay, think about your congruent triangle stuff. What's another piece of information we could state here, Sophia?
That MCK and NCK are equal to each other.
MCK and N. Why are they congruent to each other?
Because KC is a bisector.
Do we know that?
No.
I don't know if we know that yet. Okay. So I don't think we're ready to say that yet. Okay, it's probably very true, and in fact, it's absolutely true, but we don't know that it's true yet. Okay, it's going to be actually once we prove these triangles are congruent, then it's going to make it true, but we can't say that yet. Okay, so Sophia, you want to look around and call on someone that maybe can help you out? Xavier.
Segment MC is congruent to segment NC.
Okay, very good. So we can now say that MC, write this down, this is really good stuff, is congruent to NC. MC is congruent to NC. Why is that true, Xavier?
Because they're both radii.
Radii of the same circle are congruent. You guys agree with that? So radii of the same circle. There's my symbol for circle, circle with the dot in, are congruent. Okay, do we all agree that radii of the same circle are congruent? That's kind of the definition of a circle, right? All its radii are congruent. So now we can mark this side. Let me do it in red. We can do it this side here, and we can mark this side here. All right. So now we have next one. Kaylee, go ahead.
Xavier.
All right, Xavier, what do you got?
Segment KC and segment KC are congruent.
Okay. Oh my goodness, we have a bad word. Oh no, because look, we can say that KC is congruent to KC. And why is that true, Xavier? Very good. We can now say that KC is congruent to KC. And that's nice that Tess was able to construct that for us, right? And that is the reflexive property. Reflexive. Sorry, this is messy. Okay, and we already know about. All right, now, but oh my goodness, we have a bad word. We have angle side side. Oh my goodness, it's so embarrassing. Oh, we can't do angle side side in this class. Okay, that's a terrible thing. Okay. Yeah, go ahead, Xavier.
Triangle KCM is congruent to triangle KCN because of hypotenuse.
Remember, hypotenuse leg is the acceptable version of angle side side. So now we can state the two triangles are congruent, saying we can now state those triangles for me, Xavier. KCM is congruent to what? KCN. And why is that true? HL, the acceptable version of a angle side side. Now, we're not done yet. We've just proven the two triangles are congruent. So, but we've got pretty much all of the work done. So, Kaylee, pull a stick on that. Nicole. So, Nicole, remember what we're trying to prove. We're trying to prove that KM is congruent to KN. Can we say that now, Nicole? Okay, we can say that. That is an acceptable statement now. So we now have proven that KM is congruent to KN. And why can we say that, Nicole? CPCTC. Okay. Now, we can also now say that what Sophia stated is actually correct now, right? We can say this is an angle bisector because of CPCTC. We can say these two sides are congruent. We can say this is an angle bisector. So now we know they're congruent. We can say it's a kite, right? Remember kites? See that? Okay. It could be a kite. Now, if it grows enough, it could actually be a rhombus also. Am I thinking about that right? I don't know. But definitely a kite, right? And so all the things. So here's an interesting thing. If I look at diagonals, if I take a diagonal and drop it down right here, and since it maybe is a kite, what can we say about the angle where the green and the blue lines meet? Right angles, right? See that? We also know that the blue line is bisecting the green line through kite stuff, right, guys? So think about all the stuff this problem involves. It involves, first of all our good circle knowledge that we're learning right now. it also involves all our old side angle side stuff, right? Or our old congruent triangle stuff. And then we can get all our quadrilateral information in there also. So tons and tons and tons and tons and tons of good geometry in a simple little problem right here. You guys see that? That's why geometry by far is the best subject known to. Remember, guys, Book of Euclid is the second most published book after the Bible. So it's a huge, huge book. It's been around for thousands of years, and it's because of this absolutely cool stuff that we love it so much. Okay, your job is to apply it and figure out the value of x. Go. And I will say, what would we have to know here? We can assume it, but what would we formally have to know in order for this to be
There are
true?
lines of tendency.
That's C and B or tangent.
Yeah, and I'm going to say right now that they are tangent. Even though it's not a very big drawing, it just looks like it would go through. But we're going to assume that B and C are points of tangency. And so your job is to find the value of, find x, and then find the measure of AB. Okay, so you have to do two things. You have to find the value of x and find the measure of AB. Go!
No one asked for this.
In AC. You found it, Chris? You already know it.
Yeah.
This is 2.
That's the next one.
Oh.
It's gotta be more quiet. Whisper around me.
Okay, so for the sake of fun here, let's have, and don't let me forget, I'm recording this. I do not want this to be a entire day recording that I have to put on Schoolies. That would be a long way. So do not let me forget. Okay, so Kaylee, you've been doing such a nice job pulling sticks. Can you please pull another stick?
Austin.
Mr. Austin. So how would we start this one out, Austin? What did we just learn by proof?
Oh, that A, B, and AC are.
Okay, we know by what we just proved is the sides from the circumscribed, and we might want to write this down in our notes. So this is a theorem. Okay, we're going to call this this theorem. Here's what we're going to call this theorem right here. Okay, this is the word we're going to give this theorem. Okay, we're going to call it the circumscribed tangent theorem, we're going to call it, okay? So, and what does the circumscribed tangent theorem says? It says the segments from the circumscribed angle, I'm just going to abbreviate circumscribed as CIR, angle, not just this one angle, to the points, to the pots, right? Sorry, this is really messy. I apologize. And I'll say this little circumscribed tangent theorem. So I know it's confusing, right? Why am I writing theorem so many times? So we're talking about the circumscribed tangent theorem, class. Segments from the circumscribed angle. Sorry, this is so messy. This is terrible. Okay, get rid of all this mess because it's going to be on film here. All right, to the pots. What does pot stand for, class? Point of tangency. Are congruent. Okay, are congruent. Okay, does that make sense, class? So we know that this theorem we just proved that we know that these segments from the circumscribed angle, in this case theta, to these 2 points of tangency, we know that those are congruent, right? So therefore, this theorem right here that we just formally proved, we can now write an equation. You guys understand that? We can now write an equation. So Kaylee, can you please pull a stick, and this student's going to tell us the equation to write. Oh, it's Austin. Never mind. Austin, what's the equation we could write?
8x equals 2x.
Okay, so 8x equals not 2x, but what? 2x squared.
Yeah,
said
it's not
No, he didn't. Okay. Now, Austin, this should take you back to your geometry days. This is what we call a quadratic equation.
Do you mean?
Okay. So now, how do we solve a quadratic equation? The way we solve a quadratic equation is we set it equal to 0. Do you guys understand that? Especially when you have x's on both sides, we're going to set it equal to 0. So I'm going to move the 8x over and flip it. So that's going to give me 8x squared minus 8x equals 0. 2x squared minus 8x equals 0. Sorry. Okay. Absolutely. This is a simple algebra question. Okay. Now, how do we solve quadratic equations? Well, the easiest way to solve a quadratic equation is factor them. Okay. If we can't factor them, then we can use the quad formula. Okay. Or we can complete the square. But this one right here is absolutely an easy factorable problem. And then what we're going to use something called the zero product property rule. It's a very simple property rule. It's a very simple concept. It's saying this: if A times B equals 0, what do we know about A and B, class? One of them or either both of them are 0. So we either know that A equals 0 or B equals 0. Now, we want to write this equation right here in the form something times something else. Well, what is the greatest common factor of 2x squared minus 8x? Definitely a 2. What else can we factor out? How about an x? Can we factor out an x? And then we work backwards, class. So here's what we do. We work backwards. We're setting it equal to 0. 2x times what gives me 2x squared, class? X. Do we all agree 2x times x gives me 2x squared? 2x times what gives me 8x? 4. So these are our two factors that equal 0. So what you can think of it, if you're doing the zero product property rule, you can think of this yellow part as A. Will, are you paying attention? I hope you are. Okay. All right. And also Austin. And we can also think of this green part right here as B. See that, class? And the zero product property rule says when we multiply two things together and we get 0, either A equals 0 or B equals 0. So we have two equations. We know that either 2x equals 0 or x minus 4 equals 0. See that? Now, when we solve for x, in this case, what does x equal here? Divide both sides by 2. What's 0 divided by 2? 0. So there's one solution we could have. What about this one over here? What are we going to do to both sides? We're going to add 4 to both sides. So now we get x equals positive 4. Now, in geometry, we often throw out, when we have quadratic equations, we oftentimes throw out one of the solutions that don't make any sense. So we could definitely throw out the 0. Why can we throw out the 0? Rachel, why can I throw out the 0? You're not going to have a distance of 0. Okay, if your distance is 0, it makes your tangents 0, and that doesn't do anything for you. So it has to be 4. So we know that x has to be 4. You guys see that? So in this case, 4 times 8 is 32, and 4 squared 16 times 2 is also 32. So we know that x has to equal 4, and the two tangent lines are equal to 32. Does that make sense, class? Okay. All right. So we're not going, I want you guys to do this. I want you to copy this down and have this in your notes, and we'll do this as a warm-up tomorrow. Okay, this is going to be your warm-up problem tomorrow. Don't do it tonight. Don't be an overachiever. If you want to be an overachiever, do your delta math. Just have this ready to go. So, Will, are you writing this down in your notes so you have it ready to go for tomorrow? Thanks. Okay, why am I picking on Will? Well, because I don't think Will understands what we're writing this down. All right, I like Will, though. All right, so here's the deal. Will's a nice kid. All right, so now, here's the deal. See, I got that on tape, Will. So if you ever don't think you're a nice kid, I don't like you, I have it on. It's going to be on tape. And Will, if you're having a bad day and you're not sure of yourself, just watch the video and it says you're a nice kid. Okay, all right. So we all good here? Have this ready to go by tomorrow. And then that way, ladies and gentlemen, we can go into this. So this is a good application problem of tomorrow, of what we've learned. So now I'm going to stop sharing the video.